This video is about the restoration and repair of this Pioneer SX-750 receiver. The cabinet wasn't in the best condition when I got it. I've had to re-veneer the top and sides. Other work that was done on it, all the lighting has been converted to LED, and I'll describe some of that in the video. Electrolytic capacitors and some of the transistors have been replaced. I had an oscillation problem in the power amplifier section, which I've dealt with, and I'll show you that in the video. The mains switch, in common with a lot of these SX-50 series receivers, had burnt contacts. I'm now using that switch to drive a relay which switches the main current through the amplifier, and I'll describe that in the video. The power supply and protect board has been refurbished, and I also had to deal with a thermal management problem on there, which I'll describe in the video. I've added a preamplifier board so that I can derive a preamp output for my subwoofer speaker, and I also had a fault with the AM receiver chip, which has been replaced, and I'll describe some of that in the video as well. So before I dive in, just a quick look along the front panel of this receiver. Most of it's in good condition. There's one little blemish on the top edge, but the switches and knobs are in good condition. So you have the normal speaker selector, which is also the power switch, bass and treble, which are usually bypassed unless they're switched in with this tone switch, these very satisfying positive toggle switches. There's a highs filter, attenuates highs somewhat above 6 kHz, balance and volume, and then a loudness control, very common on these 70s receivers, which boosts the bass at low volume levels, and that effect diminishes as you turn the volume up. You can mono the output if you wish with this mono stereo switch. The duplicate switch allows you, if you have two tape decks connected, to copy from one deck to the other, and this allows you to monitor either of those two tape decks. Function selector and FM muting, which if it's on reduces or stops the hiss in between FM stations. So a quick look at the top side of this receiver. It's not the most friendly to work on. The power amp board is mounted to the rear of the heatsink for the main power transistors. A little bit awkward to get apart. You also have this power supply and protect board here, also mounted vertically in the receiver with many connections on the edge. This is the protect relay here. There's another part of the power supply underneath where the main rectification happens. Here you've got the tuner board, and also it has the phono stage here. There is a tone control board which you can't really see, it's down here, better access from underneath. I've also added some PCBs of my own, so here's one of them. This is my preamp PCB, and I'll just show you here what I have actually added in. That's the preamp PCB, and it just mounts to the edge of the heatsink onto some existing screws. This is the board that fits over the main filter capacitors, a bit like with the 636 I did recently. It just makes it easier to terminate all the wires rather than trying to solder straight onto the capacitors themselves. This board is for the power relay, so I mentioned that I'm now using the rather damaged power switch to drive a relay, and the relay switches the main current to the receiver, and I'll show you how this works in detail later on. This small board here is to allow me to convert the 4 single inline op amps that are in this receiver to, I think it's an OPA 604. I'll correct that later if I'm wrong, but I'm led to believe that that sounds a bit better than the existing ICs that were in there. And this board here is just a simple AC to DC board for the lighting conversion. This was actually one I designed for a Pioneer SX-450 and 550, but by complete luck, the spacing of the screw holes here matches the spacing of some existing posts that were down here. So I've tucked my board in down here, and that distributes takes in the 7 volts AC and distributes power to the 3 dial face LEDs and also to the power LED. So I'll go into some detail of how those boards have been installed now, and I'll start with the lighting. In this section I'll briefly describe the changes I made to convert the lighting in this receiver from tungsten to LED. Sorry about the rather small diagram, but I want to get all of the circuits onto one page. So first of all, this yellow line shows the supply for the selector lights. It's got its own tapping on the transformer, fused, halfway rectified, smoothed, and that gives 6 volts DC, which runs through a wafer of the selector switch and then connects to whichever of the 4 lights is appropriate for AM, FM, phono or auxiliary. Then we have the feed to the dial lighting. Now that has its own tapping on the transformer as well. That's a 7 volt or 7.5 volt AC supply fused, and then that just runs to the 3 dial lights. Additionally, there's another feed taken from that 7.5 volt AC supply through a resistor, rather bizarrely mounted on the headphone assembly board, and then that goes up to this 8 volt grain of wheat light, which is the power on indicator. Then finally we've got the circuit for the stereo indicator light. Now that comes from the 13 volt regulated supply that feeds the tuner section, through another 8 volt grain of wheat light, through a resistor, and then grounded by one of the pins on the stereo FM decoder chip whenever it detects a stereo signal. So starting with the conversion of the selector lights, the supply is already DC, which is good. I don't like running LEDs from AC because you just sometimes get that peripheral vision flicker, which can be annoying. But I did need to add some additional resistance into this circuit. Now, what I did was reroute the wiring to borrow that resistor position that was used for the power light, because I'm going to convert that later using a separate board. So I'm running my 6 volts DC through this resistor, which I've now changed to a 2.4K resistor, and that is sufficient to drop the voltage to the correct level for the LEDs. And the LEDs themselves are simply, all I've done is chop the grain of wheat bulbs off and solder on a 3mm warm white LED and add a bit of heat shrink sleeving. So the next step was the conversion of the dial lights and the power indicator light to LED. As I mentioned before, I installed my own PCB to deal with this. Very simple, it's just a bridge rectifier, smoothing capacitor, and a resistor can be added to each LED to get the brightness correct. So it takes in the 7.5 volts AC, and then each output is wired to the appropriate LED. And I'm running the dial LEDs at about 10 milliamps and the power indicator at about 1.5 milliamps, just to get the intensity correct. And the actual board sits on some existing screw holes. I was very lucky there. And the dial LEDs themselves are just simply warm white LEDs plugged into a Molex socket, which is fitted inside the original lamp holder. Now, in fact, here I've got it bent over, but in the final design, I actually folded the LED vertically up. It's one of these straw hat sort of concave end LEDs. There's quite a lot of light throw out of the side, and I found by having it mounted vertically I got a better illumination on the, or more even illumination on the dial front. And the final step was just to convert this stereo indicator light to LED, and this was quite easy because there's already a resistor in this circuit. So I just had to change that for a larger one, 3.3K, and fit my LED. And this works, but it's not quite right. When there's no stereo signal being detected, there's enough leakage through this chip just for that LED to glow softly. But that can easily be fixed by adding a 10K resistor across the LED, and then it behaves as you would expect. And that is the conversion of all of the tungsten lighting to LED complete. So the next step of this restoration of the Pioneer SX-750 is to replace the main smoothing capacitors. The originals were these Nippon Chemicon 1500 microfarad ones. I bought some new Chemet ones, same value, 1500 microfarads, but 63 volts rather than 50. Obviously they're much shorter, but they have the same diameter, so they fit in the clips okay. One of the problems, as with the 636 that I did recently, the terminals on the originals are large wire wrap terminals, whereas these new capacitors have the typical snap fit terminals. And as again with the 636, I've designed a little adapter board so that I can terminate the
wiring from the power supply straight onto the board here rather than trying to wrap it around the smaller terminals. It's going to be quite tricky to fit it in. The capacitors are terminated behind this rectifier board. The original wires went through these holes in the top here, but there is plenty of room to fit the adapter board behind. I've just got to manage to find a way of getting it all in neatly. Before I do that, I want to replace the main rectifier diodes on this. In fact, there's two sets of rectifiers here, main power supply, and behind here there's a lower current power supply bridge as well. So I'll get those changed, and then I'll come back when I've made a bit more progress. So here we are at the intermediate stage with the wires terminated on the capacitor board. I've now got to mount the capacitors and attach the board to the capacitors. Has been quite tricky. These wires are very stiff, not a lot of working room here, but hopefully when it's all put back together, the overall job will have been easier than trying to terminate those wires directly onto the new capacitors. So the cap board is now soldered in. The wires seem to fit okay. I'm now going to reattach the top, and just one of the wires, the positive, broke off from the tag here, and also this AC wire. I'll have to reattach those, and then we'll give it a test. So I'm quite relieved to say this is back together and working. The rectifier board is now installed over the top of the capacitor board. There is plenty of gap between them. You might just be able to see the capacitor board through the holes in the rectifier board there. It was quite fiddly to do, and I had a couple of wires break off from the wire wrap posts at the bottom of the rectifier board, which I've had to solder back on. But otherwise it's back together and seems to be working. I'm just looking at one of the amplifier rails. It should be plus 41. I'm on dim bulb, so I'm getting plus 40.2, which I think is fine. I'll just check one of the negative rails, though I have already checked to make sure they're all good. And yeah, we've now got neg 40 on that one as well. So I'm happy with that. Everything seems to be working at the moment. FM is working. Everything's on. But there's a long way to go, a lot more to restore, and hopefully I won't break anything along the way. So I'm back doing some more work on the Pioneer SX-750. The receiver has now been fully recapped, and some of the silicon has been changed, including the final output transistors and some other silicon in the power amp stage. The back is off at the moment because it was having some rust treatment, but also taking the back panel off does give better access to the power amp section, which is actually quite awkward to get to with the big heatsink and the actual circuit board being mounted onto the heatsink. It's actually quite fiddly to take apart. Also, with the back panel off, we've got a slightly precarious situation here with the mains input and the loudspeaker output, but it is connected and it is working at the moment. And I've just been doing some power tests, and I think I've run into a bit of a problem. So I'm just going to go a bit closer to the scope here. I've got 1 kilohertz going into the amplifier. And if I just turn up, now this is a 50 watt amplifier, so that means 20 volts RMS should be our 50 watts. And I can make that, so just looking here, we get, we're about 12, 13, 14, 15, 17, 18, 19 volts. We make our 20 volts, and then just at that point we start to see some oscillation coming in, and then on the other channel, just before it, well, probably at the point where it is clipping, or that's just before the clipping point. So I'm not too happy about that. I don't really want to see oscillation, even though it's very close to its clipping point. It is happening before it clips, and I don't think that's quite right. Now, while I'm here, I thought this might be of interest. I read online that you can use an AM radio to detect if an amplifier is oscillating. So I've got one here. I'm going to switch it on. Now, there's a lot of switch mode power supply noise in this room, so there is a lot of background noise. But if I go up to the scope now, and I will turn up the amplifier again to the point where it starts oscillating, I think you'll hear quite clearly what I mean. Here it comes.
I think that's pretty conclusive that we've got some oscillations going on, and also that an AM radio is a really good way of detecting them. So the question now is, what am I going to do about this oscillation? I have to say I don't relish the prospect of taking the power amp section apart again. I'm most worried about these STV4H diode packs, which are irreplaceable, and I did take a lot of care to try not to break the leads, but they are very fragile, very vulnerable. However, I don't think I've got much choice. I think I will have to take it apart again, and I've got an idea where I might start to look at the problem. So this is the schematic of the power amp assembly. Now, I watched a video by X-Ray Tony B where he had a similar oscillation problem, I think with a Marantz amplifier, and where he was looking was at the capacitors that are installed between the collector and base of some of the transistors. Now, my understanding is that any transistor has a natural parasitic capacitance, a very small one, between each of the three legs, but that capacitance becomes significant when it's between the collector and base, because it gets magnified by something called the Miller effect, and that's related to the gain of the transistor. So although it may be a very small parasitic capacitance, if you actually measured it, in circuit it becomes much more significant, and it reduces the bandwidth, the transition frequency of that transistor. Now that could be a problem, but in some cases it might help to damp down oscillations by reducing that bandwidth. And you can make the effect bigger by adding your own capacitor in that location. So, for example, in this particular amplifier, we've got a 560 picofarad between the collector and base of the output NPN transistors. We've got this 180 picofarads between the collector and base of each of the four pre-driver transistors, and we've got another 15 picofarads between the collector and base of the voltage amplifier transistors. So I'm going to do some experiments with increasing the capacitance in those locations and see if any of them help to reduce the oscillation problem. Next morning I've taken the power amplifier assembly apart, and I'm experimenting with different capacitors at the points that we just looked at on the circuit diagram. So I've tried an additional 470 picofarad across the collector and base of the main output on one channel. That made no difference. I've tried an additional 100 picofarads across the previous driver stage. That's made no difference. But what does seem to have helped is I've put 20 picofarads across that voltage amplifier transistor, the one that had a 15 picofarad across it before, and that was the step that seemed to make the difference. So if I go up to the scope here, and we've got the 1 kilohertz signal going in again, and I'll just increase the, whoops, it's just gone to sleep, I'll just increase the gain. Here we go, and coming up to the clipping point. Now the yellow trace is the one I've been modifying, so now we can see the purple one goes into oscillation as the yellow one just goes into normal clipping. So I'm happy with that. I'm going to just try putting that same capacitance on the other channel, and I'll just check that that cleans up both of them. Okay, I've now removed those additional capacitors that didn't make any difference, and I've put 10 picofarads across each of the left and right voltage amplifier transistors. And if I go back to the scope now and try my 1 kilohertz again, here we go, and now both channels clip and there is no sign of that oscillation. And I have tried at lower and upper frequencies as well, and it's behaving similarly. So just to round off this section, I did manage to get the power amp assembly back together without breaking the leads from these STV4H diode packs. These are the thermal sensing modules that can contain 4 diode junctions that bolt to the heatsink. I rerouted the leads to go directly to the bottom of the board. Their route to the top of the board was rather taut. I also added a little bit of super glue around the points where the wires go into the pack. I don't know if that'll help. Presumably the wires will just break a bit further down. But I thought I'd do anything really just to try and stabilise it a bit. But fortunately it has all gone back together without breaking anything, and that part of the project is now complete. So now it's time to tackle the mains wiring on my Pioneer SX-750. Now I'm not for one moment suggesting that anyone copies what I'm doing. Clearly there are significant risks in making amendments to the mains wiring on any device, but this is how I've chosen to tackle the problem on my own unit. Now the first problem, and it's a problem I found with the Pioneer SX-450 and 550 that I did as well, is that the main switch, which is mounted on the back of the speaker selector, the contacts become carbonised and high resistance and make very poor contact when you switch the unit on. So in this case I've stripped down the switch and cleaned the contacts as best I can. And also it was acting as it is a double pole switch using both poles in the live and neutral. I'm only using it now as a single pole switch, so I've connected the two contacts in parallel, and I am getting a good low ohms reading when I operate the switch, so that's satisfactory. But if I use it to switch the full load of the amplifier, it's just going to fail again in very short order. So the plan is to use that switch to drive a relay, and the relay will then switch the full load of the amplifier. Now I've read online that some people have used the switch to drive a triac, and then the triac switches the amplifier, and that's a perfectly good solution as well. It was just my preference in this case to use a relay. Now I'm going to try and fit this relay into the well here where the IEC inlet is, and in this hole would normally be the voltage selector. In fact, it still will be the voltage selector. So here's the circuit board that's going to house this relay. Nothing's soldered in yet, so I'm just going to hold it up gently. But the idea is it's going to sit directly on top of the IEC inlet. And on the board itself, we've got the relay on a socket base, and that's a 16 amp relay with a 240 volt coil. We've got a fuse. We've got a suppression capacitor that goes across the relay contacts to try and prolong their life a bit, and also a 3-pole Vargo connector to help me with the terminations onto the board. Now I'll put a diagram up of the actual wiring in a moment, but the connections that I have to manage are these two red wires, which are from the switch, and they will go to 2 of the poles of the Vargo connector. I've got ground and neutral, that's chassis ground and neutral, which will go directly onto the back of the IEC inlet pins. I've then got this grey and red wire, which are the 240 and 220 volt tappings from the power transformer. They will go back onto the voltage selector. This is a European model 220, 240 volt. And the orange wire, the input to the voltage selector, that will come from the 3rd pin on the Vargo connector, and that will be the switched output of the live via the relay.
So I'll just try to illustrate the wiring arrangements for this relay module that I'm going to install. This is the power input section for the American version of this receiver. I can't find the diagram for the UK European model, but I've just reverse engineered what I've got. So on my unit it looks like this. We've got an IEC inlet here, connection to the chassis ground, a double pole switch, this is the source of trouble, a 2 amp fuse in the live side, and then this terminal block here with a 0.01 microfarad capacitor across. The neutral side goes to one end of the primary of the power transformer, and then you have the 220 and 240 volt taps fed through the voltage selector from the live side, and in my case we're set for 240 volts here in the UK. So this now shows the relay module installed. This light green panel is the board with the IC inlet, 2 amp fuse, the suppression capacitor, the relay itself with its 240 volt coil, and that 3-way Vargo connector. Now here is the switch which I've tried to recondition as best as possible, and because I'm only requiring now a single pole switch, I've wired both of the poles in parallel. So because we know the contacts are not very good, it seems sensible to put them in parallel, get as lower contact resistance as possible. So when that switch is closed, this relay coil gets energized, and if I just go to the next slide, this path in yellow shows the current path through the switch and through the relay coil. So this is now energized and will pull in the contact. And once it does that, we then complete the current path through the power transformer, which I can illustrate on the next slide. And there we go. So the switch is pulled in, and we've now got a current path from neutral through the transformer, through the voltage selector, and through the relay back to the live side, and also through the fuse.
Okay, the relay board is now installed. It was fortunate that I put the relay on a socket base because I was able to install it without the relay plugged in. And if I hadn't been able to do that, it would have been almost impossible to get the soldering iron down to the rear of the IEC connector. But as it turned out, it all went in eventually, and I'm now ready to try a power-up test. Okay, ready for testing. I'm going to operate the power switch, and let's have a nice look at the relay and see if it operates correctly. And the relay's closed, and the amplifier has kicked in. I'll just turn that down so we don't copyright. That's good. I'm going to turn it off again. That's good, and back on. Excellent. Well, that seems to be doing what it should do. I've just heard the protection relay click in again as well. Good. I think that is working as intended.
So before I leave this section about the power supply, I wanted to make a comment about the fusing because I was quite surprised with what I found. So on the secondary side, there's a half amp fuse in the supply to the selector lights. There's a 1.5 amp fuse in the supply to the dial lights and power light, and that made perfect sense when they were tungsten bulbs. That could now be down rated now that they're LEDs. There are 2.8 amp fuses in the supply that does the plus and minus 48 volt rails. This is the low power supply to the receiver, the supply for the preamps and the tuner section. But then in the high power part of the supply, so the plus and minus 41 volts that go to the power amp stage, there is no fusing on the secondary side. I was quite surprised about that. So the only protection you have here if there is a short circuit is the 2 amp fuse on the primary side of the transformer. And in America I believe that would be a 4 amp fuse. Now 2 amps at 240 volts is 480 watts. So if you have a catastrophic short here, this transformer is going to be trying to push at least 480 watts into the receiver. And you're going to possibly have to exceed that by quite some way before this 2 amp fuse would go. It's going to need to get to sort of 2.5, 3 amps before it'll even think about melting. So this may be perfectly normal, but I was quite surprised that there is no additional fusing here to protect the high power part of the power supply. So if your output transistor's short, it strikes me there's going to be quite a lot of smoke let out and quite a lot of other mayhem before this fuse would even think about blowing, if it even does.
I'm about to do some testing on this preamp module that I'm going to fit into this Pioneer SX-750.
I'm just going to interrupt myself here because I realised I neglected to mention the purpose of this board. This is to allow me to provide a preamplifier output on this receiver. I did the same thing with the Pioneer SX-636 that I restored recently. The preamp output is an output that tracks with the volume and tone controls, but is taken off just before the power output stage. This board provides me with a buffered version of that signal so that nothing can be fed back into the power amplifier in this unit, and also allows me to add a little bit of extra gain. I'm going to present my preamp output in place of the Tape Rec 1 fixed level outputs. So I will be sacrificing those, but it will give me an output that's more useful for my purposes.
I'm using the same circuit that I used for my Pioneer SX-636 with a slight difference. Well, the layout of the board is different so it'll fit into the receiver okay. But I've also used an onboard power supply. I've got a regulated supply here with a Zener diode and a transistor. In the 636 I ran the preamp straight from the regulated 30 volt rail. In this one there is a regulated 33 volt rail, but I didn't want to add any more load to it. The transistor that provides that, I think it's Q10 on the power supply and protection board, does run quite hot, so I didn't want to put any additional load on that part of the circuit.
So I'm going to run this straight from the unregulated 48 volt rail and provide my own regulation down to, well, in this case, about 18 volts. Now, the only problem is I don't have a 48 volt bench supply to test this. Mine only goes up to 30 volts. So again, I've no idea if this is a good idea or not, but I'm going to use my 30 volt supply and get the additional 18 volts from these two PP3 batteries. So I'm going to connect up now, and I've got my 48 volt rail there. And if I move my probe onto the regulated rail, I should get close to 18 volts. Okay, 17.1. It's an 18 volt Zener diode, so then you've got the drop across the regulated transistor. So 17.1 volts is absolutely fine to run this. And it's drawing 10.94 milliamps. Now, about 6 or 7 of that is going through the Zener diode, and the rest will be providing the current for the actual amplifier itself.
So as promised, just a quick look at the circuit diagram for the preamplifier module. The difference between this one and the one I added in the previous project on the Pioneer SX-636 is that I've just added an onboard power supply. It probably was overcaution on my part, but I didn't want to run this directly from the plus 33 volt regulated rail, just because the regulated transistor in this particular receiver does run quite hot. I think it would only add about 0.2 of a watt to that, but even so, it's a very simple matter to add my own regulated supply directly powered from the 48 volt unregulated rail. So we're just using an 18 volt Zener diode and a medium power Toshiba transistor, which gives me, in theory, 17.4 volts on the output. I think I measured about 17.1 or 17.2 in reality. And then the amplifiers themselves, I'll just go to the next slide, obviously there's 2 of them. This was a building block circuit that I found on the web, and I'll put the link to it in the video description. Really useful, low noise, non-inverting amplifier with the ability to add some gain. As shown in the configuration here, we've got 6 dBs of gain, but you can vary that by changing the components that are shown in green. I've run this circuit down at 5 volts as well for a separate project by scaling these resistors, and it works really well at 5 volts too. So it is an extremely handy building block circuit, and it works perfectly in this situation where I need a high input impedance, ideally a non-inverted output, and a little bit of gain.
So at this point I was supposed to have some footage of me testing the preamp board, and I recorded the results on the scope with my camera that I normally take on holiday. Unfortunately, I then went on holiday and managed to delete the footage that was on that camera, thinking that I'd already copied it across. However, what I'll now do is just show you after the fact. The board is in and working, and if you want to see some tests on it, my previous video on the Pioneer SX-636, the preamp board in that uses exactly the same circuit. It's just that this one is on a different shape of PCB and has its own onboard power supply. But very briefly, it picks off the preamp signal going into the power amp stage, and that's fed into the preamp board here. It takes in a feed of 48 volts, which is regulated on board, and then the output passes to the resistors that normally feed the tape rec out 1. Now I'll see if I can get a video just a bit closer just to show you where those resistors are. You might just be able to see those two 2.2k resistors. They normally take the tape rec output signal to the tape rec phono jacks, and all I've done is lifted one end of the resistor and add and substitute in my feed from the output of the preamp board. I'm annoyed that I didn't put those 2.2k resistors on the preamp board. If I ever do this again, or if I'm actually submitting another order for PCBs, I might do a modified version with those in, because that looks a bit bodgy. But anyway, it does work. And while I've got the camera zoomed in and the unit turned round, I'll just go up and you can see just about the rear of that preamp board fitted in there. And just to prove that that preamp board is working, I've got the scope connected across the tape 1 rec outputs, which are substituted with the output of that preamp board. I've got a 1 kHz square wave going in, and if I operate the volume control, you can see it responds to that. and obviously balance as well. If I switch in some tone, adjust the bass boost, bass reduction, and treble boost, treble reduction, that's all responding, and also the loudness as well influences it. So everything seems to be working as expected, and I have in fact been using this now for some time to drive my subwoofer, and it's working very well. So I'm getting close to the point where I hope I can reassemble this receiver, but I'm still not quite happy with this power supply and protect board. This row of 24 wire wrap terminals here just looks a mess. Some are wire wrapped, some were soldered from the factory, and some I have soldered as I've rearranged the wiring for the lighting, and also where some wires have just broken off as I moved the board forward. I think it looks a mess. It's functional, but I'd rather replace that with a row of wire to board screw terminal connectors. The other thing I'm not very happy about is this power resistor here. Again, this is factory. It's a 5 watt 150 ohm resistor. It takes the 48 volts down to about 30 volts for the tuner section supply, and then that 30 volts is further regulated by this transistor here down to 13 volts. This is just, it's flapping about, it's near the dial string, it's near these capacitors, it just doesn't look quite right. So what I want to do is fit one of these aluminium chassis power resistors onto the back wall here, and hopefully that'll look a bit neater. I also want to try and sort the heat sinks out. We've got two transistors here that both get quite hot. This one does the regulated 33 volt plus 33 volt supply. What I'm going to do, the 13 volt one here has a taller heatsink. I'm going to move that to this position, and then I'm going to fashion my own heatsink for this 13 volt transistor, try and get some more heat away from it. I did bolt an additional piece of metal to the side of it. I don't know if you can see that there, but again it just doesn't look quite right, so I want to try and make a better job of that. Just breaking into the video here, there are a couple of things I noticed while I was editing that I forgot to mention. This transistor here does the minus 37 volt rail, and it doesn't run too hot. In fact, it originally had no heatsink on it at all. I have, however, fitted my own just to give it a bit of extra thermal protection. I also swapped out the speaker protect relay. Now, the original was okay, the contacts didn't look too bad, but given that they make an almost identical relay still with the same pin out at the base, and they're not too expensive, I thought it was worth swapping in a new one while I had the board out. So I'm going to remove this board now and see how I get on. So a lot of work has been carried out. The work area is in a bit of a mess, but I'm very pleased and relieved to say that the power supply and protect board is now back in service and is still working. So I'll just turn that down just in case we hit any copyright. The 24-way screw terminal connector is installed, and I do think that looks better than the assortment of soldered and wire wrapped tags that we had on there before. My power resistor for the receiver supply is mounted to the rail at the rear of the bracket that holds on this PCB. And for heat sinks, I've substituted the slightly larger heatsink onto the transistor that does the regulated 33 volt supply. And in the far corner, if I can get the light in, I've got my homebrew heatsink on the transistor that's doing the 13 volt supply for the tuner section. So I do think that looks better. I'm much happier with that. And the project is now nearing completion. I just have one little bit of wiring to do from the preamp outputs where they land on the power amp module, take them to my preamp board here. And then it's just a matter of reassembling the case, and hopefully that will be the next thing I can show you. One of my favourite YouTube channels is called Mend It Mark. Mark is extremely skilled at manufacturing unobtainable parts for equipment. Now I'm nowhere near at Mark's skill level, hence there's no video of me crashing about in the garage with inappropriate tools trying to make this heatsink. But what I did do, I used a piece of aluminium channel and I cut it, drilled it to mount the transistor, and I've also painted it black with some stove paint. It's also folded at the bottom with a tapped hole for mounting to the PCB in the same way as the original.
Well, I thought I was on the home straight. I've put the front on and the knobs, and it's looking very nice. But I thought I'd just try AM just before I finished reassembling. I've been using FM throughout to test it, and it seems fine. But AM, I've got an AM station tuned in at the moment, and it's very low level compared with the FM. So I don't know if you can just about hear that in the background. So I'll leave that volume at the same setting, and I will now try and tune in an FM station. It's a bit tricky doing it on its side, but there should be something up here around 106 and a bit. Where are we? There we go. And that is much, much louder, as you can hear. So I seem to have a problem with the AM section. Now, AM uses one chip, an HA1138, and I've had a look at the circuit diagram, and I'll show you that now and what I've discovered to be the problem. So here is the tuner section of the receiver, and the IC in pink here is the AM receiver chip. This is the 13 volt supply coming in from the power supply and protect board. And if I just go in a little bit closer, so we have that 13 volts comes in through a 47 ohm resistor. It splits. There is one branch to pin 12, which is VCC, and then another branch down here through a 100 ohm resistor to another pin calling itself VCC, pin 4, and through this inductor here to pin 1, which is described as mixer output. So I've measured the voltages on these pins, and pins 1, 4 and 12 are all lower than they should be. So I'm actually getting 5.8 volts on these two pins, which is fair enough as they're fed from the same point. And pin 12 is being dragged down to 10.2 volts. So something in this part of the circuit is loading the supply. Now, looking at these voltages, this one is only being dragged down a little bit, and it's being fed through this 47 ohm resistor. So I'm inclined to think the problem is going to be on the other side of this 100 ohm resistor, which is where the voltages are almost half what they should be. So what could it be? Well, there is a capacitor here to ground. That's a suspect. But actually, as it turns out, it appears to be a problem with this IC, and I started by desoldering pin 1, as you'll see in the video clip coming up. So looking at the rear of the circuit board, this is the HA1138 AM receiver chip. I've currently got pin 1 unsoldered. So if I touch the pad without touching the pin, you'll see that I've got 11.93 volts at the output of that 100 ohm resistor. If I now just slide the probe across so that it bridges the pin and the pad, I've now got 5.83 volts. So that pin, that input to the chip, is quite heavily loading that 100 ohm resistor. It's roughly halving the voltage, so it's probably going to be in the region of an 100 ohm load to ground. And if I change my meter settings in a minute, we can check that. So the power is off, and I'm looking at the resistance to ground from pin 1. I'm just on the IC pin, which is desoldered, not the pad. And indeed, we've got 117 ohms to ground. So that's why I was getting about half the expected voltage at this pin. Its resistance to ground is of the same order as the supply impedance, which is that 100 ohm resistor in series with 47 ohms. That's also going to be affecting the voltage on pin 4 and 12 as well. So the chip's faulty, and I'm going to have to head to eBay to try and find a replacement. So the new HA1138 chip is in, and I'm very pleased to say it seems to be doing the job. I've got my AM reception back, and it's nice and loud. And if I check the voltages around the IC, so going on to pin 1, which should be 10.8 volts, if I can get onto it, yeah, I've got 10.9, which is good. And the supply came in on pin 12, I think. If I check that, should be 11.9, and indeed 11.9 or nearly 12. That's fine. So the new IC has fixed the problem. I'm happy with that, and time to move on and reassemble the unit. I mentioned at the start of this video that I'd changed some op-amp chips in the receiver. Now, I'm not sure whether it was worth the time and trouble, but it struck me that putting in a more modern audio-specific op-amp might give a better sonic performance than the original op-amps that were in there from the mid-70s. There are 4 of these TA7136 chips,
2 in the phono stage and 2 in the tone control section. And the ones in the tone control section are in circuit all the time, even if the tone controls are bypassed. Now if I go in a little bit closer, because it's difficult to get all 4 on the screen at one time, the voltage rails for all 4 of those chips are set up by these 2 Zener diodes here. So this one derives a minus 19 volt rail, and this one derives a plus 21 volt rail. I don't know why they're asymmetric. There must be a design reason, but I don't know what it is. But anyway, the point is those are quite high for a lot of op-amp chips. Plus or minus 15 volts or plus or minus 18 volts seems to be a common maximum voltage range. So the op-amp you choose has to be able to work with those voltages, or you could change the Zener diodes and adjust the voltage rails. But I chose an OPA 604 chip, which has a wide voltage range of plus or minus 24 volts, and it also has recommendations for audio applications. Now the next problem was to adapt the 8-pin surface mount chip to fit in the space where the original TA7136 IC was, and that was just a matter of making a very simple adapter board. Now you notice here that pins 1 and 5 are not connected. Pins 1 and 5 are for offset voltage adjustment, and on the data sheet for this chip it actually tells you really don't need to do that. It says for most applications you can leave the external circuit unconnected. So that's what I've chosen to do in this case, just to keep things simple. And here we see the board fitted into the unit, or one of the 4 boards, and it slots in reasonably well. So there's just one more component I wanted to talk about. In common with other Pioneer receivers, this one uses the 2SA798 dual transistor package in the power amp assembly, and these are susceptible to becoming noisy with age and should probably be replaced. Now this is the differential pair. My understanding of this is not definitive. Please watch X-Ray Tony B for the best explanations of how these things work. But my understanding here is this is where the input signal meets the feedback signal, and then what's left is what gets amplified. So it's important that these 2 transistors are well matched, and also that helps ensure no excessive DC offset throughout the chain. So one way of making sure they are matched and they thermally track is to put both transistors into one package, and that's what this particular transistor does. It shares a common emitter, as you can see here in the circuit diagram. Now you can't get these anymore, so the best you can really do is to find 2 well matched transistors and try and put them in thermal contact. And a good pair to use is the KSA 992 pair. Now I bought some thermal glue some time ago, which was very expensive. I forget what it was, but because the glue is expensive and the transistors are cheap, I made up about 20 or so of these pairs, and it basically does a very good job of replicating this 2SA798 chip. But you do have to do some bending and twisting of the legs to get everything to connect, and I can show that in these slides. So this is the pair that I've actually fitted, or one of the pairs I've actually fitted into this receiver, and you can see by adjusting the legs and sleeving them as well, just to make sure you don't get any shorts, you can make them fit in. But it is also worth noting that on the silk screening on the PCB they have provided for fitting 2 individual transistors. So maybe the thermal coupling isn't quite as important. You could use 2 separate transistors, and that should work as well. So I've been using this receiver as my main stereo for some weeks now, and I must say I'm very pleased with it. It's nice to use, the knobs and switches have a good feel, it looks pretty cool, and also sonically it's excellent. Now it's not to say that it outperforms the 636 that I did a little while ago. That's a 25 watt per channel receiver, and this one of course is a 50 watt per channel receiver, but those powers are irrelevant in a room this size. I'd never get anywhere near 25 watts per channel, it'd be deafening. So yeah, I'm happy with the outcome of this one, and I'll be continuing to use this receiver for some time yet as my main stereo.